this is a bit of a journey really through stuff that I've just learnt over the years, all to do with spin. And if you think about, it's nearly 50 years now when Apollo 11 landed on the moon. And if it wasn't for a proper understanding of three-dimensional dynamics, then there's no way that that could ever have been done. And the idea that people knew more about three-dimensional dynamics back then than now is just the sad fact that we've lost all the stuff about spin from school syllabuses. And I guess this is a little journey to have a look at what we're missing out on. And we'll start with some stuff on bouncy balls. Now, forgive me if some of you will have seen some of this stuff before, because there's only so many things, so many fun experiments you can do, but they're good fun, worth doing, even if you've seen them before. Particle theory of light. We know about particle theory of light. Imagine this is a photon. It strikes a mirror, another mirror, another mirror. This is like a light pipe, an optic fiber. And so we want to do this experiment with actual particles. Now, I'm going to make myself a couple of mirrors here. There's one table here, table there. And I've got a bouncy ball. Yeah, the bouncy ball. And I'm going to chuck the ball under the table. It's going to bounce through. It's going to come out through this gap, through the glasses. Okay. And I can do this because it's quite a predictable experiment. This. It's just going to, ball's going to go out there. Okay, so, and the ball comes back to me. Now, okay, easy enough experiment, but why? Now, what tends to happen is that we want to go straight to maths to find out answers. There's going to be very little maths in this talk. It's all going to be about what you can do with your eyes. Because I think that if we can do things with our eyes and our brains and not need maths, then there's real scope for being able to present what are quite complicated concepts in really junior levels of science and physics at school. So we've got this kind of thing happening. There's 3 bounces and the ball is coming back to me. You can hear the 3 bounces. Ba-da-dum. 3 bounces. All right. What is happening on each of those bounces? First bounce. Well, we know when a plane comes into land, the wheels on the plane start to turn. And we'd be really surprised if a plane comes into land and it hits the runway and the wheel starts to turn. We'd be really surprised if the wheel didn't turn. So it's just intuitive that the wheel turns. So why shouldn't a ball start spinning when it hits the ground? Well, it does. And if you look, the ball starts to spin. And there's balls here you can take away with you at the end of the talk. Try it for yourself. You see that the ball starts to spin. If the ball is now spinning, we then have a situation of, well, it looks like we've got top spin on that ball. And if you have top spin, what happens? Well, is it top spin? So the balls come in. It's actually backspin. Well, what we have to do is heading towards the green mirror at the top. We have to tip our diagram upside down. Now we can kind of see that it's backspin, because we've got this ball which is spinning, going towards this green mirror. And with a bit of backspin on there, the ball will come back to me. But if you look closely, the ball changes its spin direction as well. So the ball is spinning one way. It hits the table, grips, and turns around. We can kind of explain why it changes direction, but that it changes direction is very easy to see, just with a ball bouncing. So we've got the ball coming along, and it comes back kind of the way it came, spin direction reverses. So now let's recap. The ball comes in, turns around, starts spinning, back spin, spin direction reverses. Now we've got top spin, and it shoots out this direction. Now all of this kind of, think, well, okay, that makes sense, but how do I know it's really happening? If we do an actual simulation of this, and actually the equations are really simple. Kinetic energy, half mv squared, angular kinetic energy, half j omega squared, conservation of energy at each of the three collisions, and then conservation of angular momentum about the point of contact. Well, those sums there give us those angles, those sums there give this motion is entirely described with conservation of energy, conservation of angular momentum. And all you need is addition, subtraction, squaring, square roots. That's it, solving simultaneous equations. And you think, well, okay, let's look at this more closely. High-speed camera. And these days, God, you can do this on your bloody mobile phone. This is what happens. And you think, hey, this is exactly what I predicted would happen. Well, I reasoned without doing any equations, nothing at all. And kids love playing with bouncy balls, and it's just a fun thing to do. And of course, if you then go to something like this, which was a big issue in England, I guess some of you might have spotted that here too, this disallowed goal in the World Cup. And well, what's curious about all this is that there were thousands and thousands of column inches in the media about this disallowed goal, and not one of them mentioned angular momentum. And it's funny if it wasn't funny, if you see what I mean. It's just really sad that somehow when we want to talk about something like angular momentum, oh, no one will want to read about that in the newspaper. But actually, this is just so simple. You don't need equations. You just need to think, oh, God, that's interesting. I didn't know about that. But there was not one mention about it anyway. At least there was, I didn't see it. And, okay, why? Well, part of it is that spin is thought to be complicated. Why is it thought to be complicated? Well, let's go back to one of the very first things that we might see as kids or as parents, spinning top. I mean, think, good, I know, lovely spinning top. It's colourful and it makes a nice noise. And how does it work? Why does it stay up? Well, the problem we've got is we can't answer that question simply, which means that we wait until perhaps a few people have got into university to study physics, and maybe even then they probably don't get the answer. Why, for instance, does it not stay up when it's spinning slowly? What is the critical speed at which it needs to spin before it will stay up? Why bother asking these questions? And certainly not when you're 5 years old. Because we don't bother asking those questions, for instance, in biology. My kids have all finished primary school, and they knew about DNA by the time they finished primary school. And they knew about genetics. They knew that tall parents had tall kids. You know, these kinds of things. They knew that if they wanted to find out more, they could Google genetics. They could Google DNA. Imagine if all they knew to Google was tall kids or tall parents. I mean, so I Google spinning top, and I can get one at Argos for £4.99 or something. What do I do to get more information? Now, I don't need to say very much. I just need to plant a word. And people think, oh no, people don't want to say this. It's too complicated. It sounds terrible. Well, genetics is not a very easy word. DNA, what does DNA stand? That's allowed, but this isn't. I don't understand why not. These experiments are so easy to do. And we could go even further and talk about gyroscopic precession. Not very much, but just means you can Google these words, and then maybe some people might think, oh, I've heard about precession of the equinoxes. And you think, oh, do you mean the Earth is a bit like a spinning top? Ah, good, okay. We're getting linkages. And we do that in biology. We say that mammals, we teach in primary school, are like sheep and goats and humans, share common attributes. Well, we don't have to go into the details, but it's just nice to know that there's word mammals. There's word gyroscopic precession. let's throw that in. Then we can start looking around at other things that share the gyroscopic precession attributes. Now, a bike wheel, this was probably going to be chucked in the bin. A lot of these experiments are cheap experiments. Okay, so we know about a bike wheel, but I can take a bike wheel, I can roll it too slowly and it falls over. But if I roll it fast enough, it stays up. Like this. If I spin this fast enough, it stays up. And then I know lots of you will have done this, and it's good fun. We attach a handle onto our bike wheel, and we get the gyroscopic precession classic experiment. Got a string on the handle, and I can spin this. Right, I get my gyroscopic precession going on now. Most of you will have seen this, but let's just get the parallels, because we want joined up thinking from 5-year-olds and younger, and parents. These two are the same, are they? Well, I can make this into my spinning top. There it is. That's the same as that. Whoops. Trying to do two things at once. And then I can make this. I can make this into my bike wheel precession by attaching a piece of string. So that is doing what the bike wheel did. Now this piece of string came out of the bin at Christmas time. Why these tops don't come with a piece of string attached, I don't know. It's just unfortunate that we don't. So the linkages start to become really fun in their own right. And if we do all of these things, these cheap experiments, then of course it becomes easy to put them into primary school syllabuses, because I've not done any equations yet, not one equation. I haven't done anything that mums and dads can't understand. But now I want to start getting into some terminology which I feel is helpful. The word moment or torque, that seems to be what we all like to use a lot. I prefer the old-fashioned word which was really introduced in the 19th century, this term a couple, because it conjures up what a moment really is. It's a couple of forces. And if I think of the bike wheel, I've got a weight force acting in the middle and a tension in the string. When this is spinning, what we know from Newton's second law of motion is that this is in vertical equilibrium. It's not accelerating downwards or upwards. Therefore, the net force must be zero. Therefore, the weight downwards must equal the force in the string. And you think, well, I don't know, how can that be? Because this thing looks like it's some kind of gravity-defying device. Surely the string is not carrying the weight. Well, it is. If I let go, it drops. Okay, now, you can get a spring balance, and measure the weight. Now, that's an illuminating thing. Those of you who remember Eric Laithwaite's Christmas lectures from 1974. The one thing that he didn't do when he was doing his experiments on the television was to put a spring balance on and just show that the weight didn't change. Because he did this experiment with a very, very heavy wheel, which you can't hold up because your wrists aren't strong enough to provide the couple to hold it up. But once it's precessing, then you can hold it up with a piece of string. So you don't need strong wrists, you just need a fingertip. It looks to a camera that suddenly this has got lighter. And that was proof enough, but spring balance tells you that it's not lighter. It's amazing how you can lie with physics. Magicians do that all the time. Things are really quite simple. Now, if we then go on to explaining the gyroscopic effect, it really helps to have it clear in our mind how circular motion works. And I don't like the word vector, because the word vector is a bit like the word calculus. It just turns people off. It's a foreign word. And I don't know what's wrong with the word arrow, because people know about arrows. And a vector is an arrow. So I've got some arrows here. And if I just talk arrows, I say, here's an arrow, and it tells me which direction I'm going. There we go, it's an arrow. Everyone knows what arrows are. And this is a smaller arrow. Tells me I'm not going so fast. Okay? That's fair enough. And this is a force. Tells me which direction the force is being applied. And if I apply my force in the direction of my travel, then I'm going like this. Force in that direction. Whoop! I'm now going faster. Okay. So you can just add these arrows. That's fine. Kids like arrows because they can draw them on their PowerPoint presentation. They're arrows. You can select them. You can't select vectors. Right, so I've got this arrow. And then I think of sort of rugby tackle. And I say, well, here comes this force, but force is coming in sideways now. And these arrows add together. That's fine. And of course, it's vector addition. And now we've got Pythagoras. You think, oh, wow, there's actually a use for Pythagoras theorem. And the arrow goes into a new direction. And this is what's happening in circular motion. Of course, we know that. But talking about it in terms of arrows is it's just quite handy. The power of that centripetal force, the magnitude of it, and I do talk about centrifugal force. Once you get to university, you have to talk about centrifugal force, particularly in engineering, because it is a real force. It's no less real than gravity, because Einstein clearly says that you can't distinguish between gravity and acceleration. And if you buy an accelerometer and tip it upside down, you measure 2g. You just can't distinguish acceleration from gravity. So if you're in an elevator, you feel acceleration, you feel the force on your feet. But actually, how do we know right now that we are not accelerating up at 9.81 meters per second squared? So if there's no such thing as an inertial force, as centrifugal force, then there's no such thing as gravity, which is fine. You can try working that one through your syllabuses. So you've either got to accept that gravity is a real force and that centrifugal force is a real force, or that neither are. That's my view. And we'll leave it there, Paul. I think it's... now what I want to do is to show the power of that, the magnitude of that centrifugal force. And once you start talking about centrifugal force, it makes the sentences much easier. I mean, can you imagine reading in the newspaper, grandma dies in horrific accident on roundabout when the door flung open due to the rotating frame of reference in which the force can be represented as a vector. Centrifugal force, that's what you call it. And this is the magnitude of that centrifugal force. That's 2 litres of water, that's 2 kilograms. And it's a tennis ball, weighs 90 grams. And it's just a big force. And kids look at that and think, wow, I didn't know it was so big. And you think, how can you pick up that 2 litres of water with just a tennis ball? And it's a very simple experiment. It shows that those arrows are real. It shows then that actually, I think I understand arrows now. And we've not done any maths, because we haven't told anybody that actually arrows is part of the further maths syllabus. We're just talking about them arrows. So we've got this force at right angles to velocity, speed stays constant. Now why that's important for gyroscopic effect we'll come to in a minute. Angular mass is pretty important as well. And again, it's you can do a lot of simple visual experiments, and you can get kids to feel these things, again, without going into much maths at all. Angular mass, do we have to call it moment of inertia? I don't think we have to. But you can just take a couple of these things, and it's just, you feel it. You get the kids to, oh, golly, that really feels heavy, but this doesn't, it feels light. And the concept, just feeling it, makes such a difference. Gee, I can change my angular mass, but my linear mass stays the same. Doesn't make any difference to this. But boy, it doesn't make a difference to this. And you can do it really quickly. And you can see, I mean, you don't even have to be doing it. You can see it makes it. And you start thinking, wow, angular mass is different from ordinary linear mass, moment of inertia. And then you want to get into angular momentum. Okay, so you're doing this with older kids, but it's still well worth having angular momentum in your toolbox. And then you have the classic angular momentum is angular mass times angular velocity, and the conservation of angular momentum. Well, it's a really good idea to get some of your designer technology kids to make up one of these. It's got a skateboard bearing in there and a couple of planks of wood. And it just makes it, you can have quite a few of these in the classroom. Better than office chairs. They have distinct advantages because you can be standing up straight when you're doing these experiments. And when you stand up straight, your moment of inertia is quite small. When you're sitting on an office chair, your moment of inertia is a bit bigger because you've got your legs sticking out. So I can get myself going here, and then I'm standing up here because you can't see the floor from the back. But that's what I usually do. I like standing up on benches. But you can see that conservation of angular momentum. Now, with a nice frictionless tool like that, you can see that you can do it so gently. What you have to do with an office chair is you have to spin around quite fast and people fall off, and it ends up being, oh wow, isn't this fun, and you forget the physics. But this you can just quietly demonstrate the physics. Then you can get some Winter Olympics videos, and you see here, well, this ice skater, she's got not much friction at her feet. Now she gives a kick off. Now she stuck her bum out under large angular mass and now stands up like a pencil, small angular mass. And, well, you can just do that. It's easy to do. I'll do that one on the ground because it's safer. So I can stick my bum out and then when I stand up, you can do it easy enough. And you can only do that. You can only do that really on this swivelly thing, and it's peanuts in cost to build, and it's fun. Then we get to this conservation of angular momentum thing, which, wow, the more you look at it, the more beauty there is in this stuff. You look and look and look, and you just don't stop finding amazing stuff. So I'm a space telescope, and out in space, there's not much friction. There's no friction. There's nothing to push on. And over there is a star. There's a better looking star over there. And I'm going to... How do I turn around? And you can get kids trying this. So you think, right, conservation of angular momentum is the problem. Or is it the solution? Well, if I take with me a wheel, then I'm not standing on the stool. I can spin the wheel that way, and because I'm standing on firm ground, I've provided a couple to get it to accelerate in that direction. But what if I'm standing on my swivelly stool? I can't push on the ground, so it provides an equal and opposite couple to me, and now I can turn around wherever I like. Conservation of angular momentum. If this wheel turns clockwise, I have to turn anti-clockwise. And it's the same with you're in a boat and you throw a passenger out forwards, the boat goes backwards. This is what happens. And you see all these fails on YouTube when people try to jump off a boat and they end up pushing the boat back the other way, and it just makes sense. Well, it makes sense in angular momentum as well. But that's not the fun bit. This is the fun bit. Supposing I call that clockwise, then I spin anti-clockwise. Supposing I call this anti-clockwise, then I'll spin clockwise. But what happens when I'm standing on that stool, spin this clockwise, and I turn it upside down? Because now it's spinning anti-clockwise. So what's going to happen when I'm on my stool? Well, I guess you know what you think ought to happen, but does it really happen? Let's have a look. So I spin the thing clockwise, and now I tip it around, and now I go anti-clockwise, and then I can tip it back up again. And this is how you control the position of telescopes in space. So you can point a telescope whichever way you like by having spinning objects where you have control over angular momentum. And again, how this experiment is not a difficult experiment to do, and provided you don't do it on standing on a table, it's pretty safe. Conservation of angular momentum. Angular momentum is an arrow because you have to think of it like that. So that's where you start getting, what do I mean? What is the arrow? So you see that the arrow is pointing upwards. You've got to get into the right hand thumb rule. Well, now we get on to conservation of angular momentum with cream and strawberries on, because things don't behave the way you expect. Now, I have a tennis racket here, which is red on one side, white on the other, and I can spin it, and it spins at a constant angular speed. If I did that out in space where there wasn't any gravity to end my experiment, or if I throw it really high, the angular velocity stays constant, spin stays constant. And the same is true if I spin it like this. It pretty much spins steadily. But if I spin it about this axis, something funny happens. The red side is facing you. Toss it up, and when I catch it, it's now the white side. Toss it up, it's now the red side. It won't spin stably like that. And it appears that angular momentum is not being conserved. Surely it must be being conserved. Well, you can do the same demonstration with a book. You put a rubber band on it to stop the pages from flying open. So this axis is fine, and this axis is fine, but this one, the book will always come back upside down. And in fact, if I do a double, throw it up higher, it'll do a double spin, so it's upside down now. Still upside down, because it's done a double spin. Still upside down. Now try and do a triple. So it's done a triple. Now, why gets complicated, but so's DNA. It doesn't stop you from getting your mobile phone out and saying, wow, when I catch it, it's upside down. And every kid's got one of these mobile phones, and you've all got one. It's just amazing. It just does it. It's the right way up there. And I'll toss it up. And now it's upside down. It just does it. And you want your kids to go home and try it. Just like dropping a cat upside down, you do it over a nice, soft bed or something. But, well, conservation of angular momentum, the little bit of physics comes in here. I'm going to throw this in for you guys, because this is just beautiful. I'll whiz through it quickly because I don't want to waste too much time on maths. But kinetic energy is half mv squared in a linear case. It's a half j omega squared for angular kinetic energy. In 3 dimensions, you add the three components. So imagine I've got a body spinning I, J, K axes, omega 1, omega 2, omega 3. Kinetic energy is a half A, moment of inertia in the one direction, omega 1 squared, plus a half B, omega 2 squared, plus half C, omega 3 squared. I like to use A, B, and C instead of having I1, I2, I3. The fewer subscripts you have, the less confusing things are. So that's kinetic energy, and that must be conserved in the motion when you chuck something up in the air. Angular momentum is moment of inertia times angular velocity, but it's a vector quantity. Now if I look at the magnitude of there's my angular momentum. Magnitude of that is the square root of the sum of the squares. So there it is, sum of the squares. And the kinetic energy I can multiply by 2. Now if I said instead x, y, and z instead of omega 1, omega 2, omega 3, you'd recognise those perhaps as the equations of ellipsoids. You'd certainly, if I got rid of this bit here, you'd recognise this as the equation of an ellipse, ax squared plus by squared. And if a and b was the same, you'd recognise it as a circle, x squared plus y squared equals r squared. So this is an ellipsoid, this is an ellipsoid. Both of those quantities have to be conserved, and when you draw the ellipsoids, they intersect. And if they intersect with a funny long line like this, then you can get widespread tumbling motion. If they intersect in a small place, you get less widespread motion. So if you go to Google, type in my name, go to my webpage, and there's all sorts of stuff. You can have a look at my various documentaries if you like, Dambusters and Zeppelins and stuff, but there's the one you want. So you want to have a look at these. And this shows you can click on these links here, take you to proper animations of them, and I can look at this one. And what you notice is that this is the intersection of the two ellipses, which means that if you started off in that kind of area, the two ellipses intersect in a relatively small zone. So when you toss the book up like that, it wobbles a bit, but stays more or less where it's meant to be. If you go to this one, then now the intersection of the ellipses is down here. Again, it wobbles a bit. It's wobbling around a bit, but more or less stays pointing in the right direction. But the one with the spinning around the middle axis, the intersection of the ellipses has this long space here. So it starts off spinning about that axis, tumbles around, and ends up spinning about the other axis. But it doesn't stop there, it keeps on going around and coming back. It's just like an inverted pendulum, but with a couple more degrees of freedom. Inverted pendulum starts off there, swings, comes back. Then swings, comes back. Always comes back to the same position, but from a different side. And it whizzes through quite quickly. So that's what it's doing. And I think thinking of it in terms of those ellipsoids, for me, that makes things easier. So I did say we were going to practice on a soft bed. Well, dropping cats is actually very illuminating. And these days kids have got the means to record it. Now, cats don't mind actually being dropped. If you've got a cat that trusts you, they're absolutely fine. And our cat, if you do this, you drop the cat onto the bed and it just straight away starts to claw the bed. You think, oh, good, do it again. Okay, after 3 or 4 times, it gets a bit cross. But they don't mind it too much. But conservation of angular momentum, the head end of the cat is going clockwise, the tail end of the cat is going anti-clockwise. It's actually the cat's doing something even cleverer, because in 3 dimensions, the cat not only controls its upside downedness, but it wants to get its feet to land back back feet to land first. So it controls its angular velocity this way as well. So it's doing it in 3 dimensions. Trampolines are pretty good with that kind of thing. Now, I can do that too. That's it. Oh, well, yesterday was very funny because I was in the Trinity College and I had the privilege of, oops, it's very hard to do this from up here. I should try getting down. I was in the Schrödinger lecture theatre and it didn't escape somebody's attention that this is Schrödinger's cat. So that was great. Anyway, that's an aside. Oh, look, in the old days, this was before video, you had to take lots of flash photographs. So this cat had to be dropped hundreds of times. So I think cats have got a better life now. So my body goes in the opposite direction to my arms. But if I put my arms in, angular mass is different. So I can go out, in, out. So I'm going around when it's out and back when it's in. Out, around, back, around, out. So this is what the cat is doing. So you can turn around without the wheel. But from an engineering point of view, having flying arms like that out in space would be less easy than spinning. And I do want to, I'm winding up now. I'm sorry things have run on a bit, but the gyroscopic effect with arrows, it's not scary. It's just not scary. Circular motion, do you remember learning circular motion for the first time? I just didn't get it for years. It's not easy. And this isn't easy either, but think of it with arrows and you're fine. We have a couple, as I was saying before, and using my right hand convention, the couple is pointing in that direction. Why do we have a right hand convention? Well, why not? It works. Why is I the square root of -1 and complex numbers do amazing things? Because they work. There's no such thing as I. There's no such thing as a vector, but they work. In maths, we've got all these constructions that happen to work. So if they work, let's use them. So there's our couple. Goes around that way. So I've got an arrow representing the couple. Where's my arrow? Where's my couple? And here's my angular momentum. Remember my good old arrow for speed? Well, here it is, angular momentum. Why that way? Because with my right hand, that's the direction. Now, what happens when I add these arrows at right angles? Circular motion, the arrow changes in direction, doesn't change in magnitude. So that means that my spin arrow changed from there to there. But now the couple has rotated around a bit, so it keeps on doing exactly that. So this motion is just adding the arrows. Now, people say, oh, but surely gravity is pulling it down. Why doesn't it fall down? So, well, for the same reason as a glass of water on the table doesn't fall down. It's in equilibrium, vertical equilibrium. Said, oh, but it should fall down. Okay. If it fell down, then where's my angular momentum arrow? It's that way. And did I ever provide a couple that way? No, because this string doesn't provide a couple that way. It only provides a couple that way. So the couple is that way. And lo and behold, that's exactly the direction the wheel turns to. And now the couple's that way, so that's the way the wheel turns to. It's just going the way you're telling it to go. Arrows. So gyroscopic precession, adding arrows, sorry. There we go. So angular momentum, couple, gyroscopic precession. And I have to finish with my boomerang because I love them. Another thing we can spend hours talking about is how best to explain aerodynamic lift. But I just cut the crap and say that Newton's third law, every action has an equal and opposite reaction. If I manage to accelerate air downwards somehow, don't care how, I must have a force upwards. because you can't push air downwards and not have lift on the wing. If you really want to go into Bernoulli and stuff, then just tread so carefully, because Bernoulli is such a bad explanation for lift. There was this one, everyone says Bernoulli lift. Well, if that's the case, then why doesn't it work if I blow vertically down on my piece of paper? Because I've got fast air down there, slow air down there. Why don't I get lift? And then, why do I get lift if I put a little bend in my piece of paper? Now I get some lift. It's this thing called the Coanda effect. Bernoulli effect. Bernoulli is afterwards. Anyway. But just Bernoulli is a bad way to talk about lift. So, boomerang, direction of travel. Oh, why do I have a cross-shaped boomerang? We love symmetry. This is a really good opportunity to talk about symmetry with your kids. This shape has got some symmetry, but this has got more symmetry. We know that the centre of mass is in the middle. The X shape is easier. The circles are easier than ellipses. Triangles, equilateral triangles are easier than ordinary random old triangles. So this has got lovely symmetry. Makes life easier. Direction of travel and spin. Well, we can see that the top parts of the boomerang must be going faster than the bottom parts, because just adding relative velocities. And it's another good opportunity to talk about relative velocities. So once you start adding these arrows, you get a bit of fun as well. So we've got faster moving at the top, slow at the bottom, more lift at the top, less lift at the bottom, because a faster moving aerofoil generates more lift. And so now we've got a combination of a couple, because we've got the mean value of these two forces add together to produce a net force, and the difference between them produces the couple. The net force is what you need on a boomerang for circular motion, and the couple is what you need for the gyroscopic effect. So it's beautiful. You get mv squared over r and j omega omega, the gyroscopic thing, happening both at the same time. You can give it a go. Oh, I'll do it again. Oh, there we go. Rightio. So we've got the couple and the spin right angles. It looks like the bike wheel thing, gyroscopic precession. And if you just had the centrifugal force, the circular motion, mv squared over r, the centripetal force to take you around the circle, then it's like going around a roundabout and always pointing north. Doesn't work, because you can't reverse around the other half of the roundabout. You've got to turn around the roundabout. The boomerang's got to turn around its circle. The gyroscopic precession is needed. Now what's neat is you can come up, go to the website, my website, it's not actually particularly rigorous proof, but you come up with a nice result that the radius of flight of the boomerang depends on its moment of inertia, density of air, lift coefficient of the wing, 3, and the radius of the actual physical boomerang. And all of that you can't change by throwing faster or slower. That is a fixed constant for the boomerang. Which means if I throw it slower, I'll stand in exactly the same place. Notice the boomerang nearly touched the board, the front. This time I'll throw it a bit slower. It just doesn't come back to me, but it has the same path radius. Wow, victory for maths. What you have to get is another equation which says that the spin rate is proportional to the forward throwing rate. So if you want to throw it faster, you have to spin it more. And all of this is just lovely, simple, elegant fun. Very good fun, because you can have a lot of fun with boomerangs, or you can go and make your own. These little ones, you can make them. They're easy instructions on the website. These little ones, they take about 20 minutes to make, and they they come back more or less. This one has been well and truly chewed up by my cat. But don't throw these with cats and dogs around. Look, really have fun with this stuff and go to my website, and thank you for listening.
I think lots of people will be going to your website and
to lunch.
And to lunch. Okay, and the last thing between you and lunch. But remember, we will have the video presentations on talkphysics.org. Okay, so you can see it. Now, just one last thing before we let Hugh go. He will be around for lunch. Just as a memento of his first time to Ireland and indeed his first Scrum Choose Physics, I want to present to him this beautiful book, which is an amalgamation of art and science that was created by a former employee of the Institute of Physics that lots of people here will know, Alison Hackett. So
fantastic.
I hope you really enjoy that. And thanks for coming. Yeah, don't be thrown out.
Oh, it violates them.
Right, great.
Thank you very much.